In the last section, we learned how to take the double integral of a function over regions that are not rectangles. A few of our examples were over disks, and that's a pretty common situation. Circles tend to be pretty common shapes in various applications. However, as you might remember, those examples were not the easiest ones we had. We would take a function like x squared plus y squared equals 4, and we'd have to solve it to get functions. So we'd solve maybe for y, and we'd get an equation like plus or minus square root of 4 minus x squared, where we'd have to treat this as two functions, and we're dealing with the square root and all that kind of stuff. These are not the easiest functions to work with, and especially not to integrate them. And I even avoided any examples where we would need to use something like trig substitution in order to do the integration. Let's find a better way to handle disks and circles. Well, one thing, when it comes to circles, especially circles that are centered at the origin, one common idea is to look at polar coordinates. Now, you've almost certainly seen polar coordinates before, and especially if you took Calc 2 here at Wichita State, we do talk about polar coordinates and even find the areas in polar coordinates. I think this is in chapter 8 or 10, something like that. But let's give a quick reminder of how this all works. So we'll draw in our regular x and y axes. If we look at a point in the plane, we usually give it coordinates x and y. If we drop a perpendicular down to our x-axis, then the x here represents the distance along the x-axis that we have, and the y represents the distance from the x-axis. Or we could do the same thing with dropping a perpendicular to the y-axis. In polar coordinates, what we're going to do is we're going to give this coordinates of r theta. R is going to represent the distance directly from the origin to that point, and theta is going to represent the angle that that line makes with the positive x-axis. Now, I've drawn this here in the first quadrant, so this angle is between 0 and pi over 2, but we are allowed to look at any angle from, well, actually we can look at any number for an angle. We might actually have to end up going around the origin multiple times if our number's too big or something like that. But that's the basic idea. Now, drawing it in the first quadrant does allow us to derive various formulas that will actually hold true even if we aren't in the first quadrant. But we can use the fact that we've got this right triangle here to derive some formulas. So things like from the Pythagorean theorem, we have r squared, the hypotenuse of r is x squared plus y squared. If we look at the various trig functions of theta, so you could say the tangent of theta. Remember, tangent is opposite over adjacent, so this would be y over x. If you look at the sine, or let's start with cosine. The cosine of theta is the adjacent over the hypotenuse, so cosine of theta is x over r. If we move the r over to the other side, then we have that x is equal to r cosine of theta. And if we do the same thing with sine, sine is opposite over hypotenuse, so we get y is r sine theta. These are various ways of switching between polar and rectangular coordinates. Now, you might have to be a little bit careful sometimes with finding out what theta is. You might have to pay attention to what quadrant we're talking about. So, say a point over here in the first quadrant has y over x, a positive number, whereas in the third quadrant, it's also a positive number. So, we might have to distinguish between first and third quadrant if we're using this tangent formula. And the same thing with second and fourth. If we use these other ones, trying to find cosine and sine, those have different rules about where they're positive and negative, so those might actually be a little bit more useful in some cases. But all that's getting into just some some trigonometry ideas, and I don't want to review all that right now. And it's not really going to be super relevant to what we're going to be doing with this stuff. When we talk about polar coordinates, we can actually describe various regions using polar coordinates very nicely. So let's take a disk, and that was not a very good drawn circle. And it's still not very good, but oh well. Let's say that's a disk. And instead of using little r for our radius, because we're using a little r for our coordinate, I'm going to say this is a disk with radius of a. The disk with radius a can be written as r theta, where the r values are between 0 and a. So a 0 down here at the origin, all the way out to a. With theta, we could just take all possible angles, but normally we'll go ahead and restrict it from 0 to 2 pi, just because we don't want to end up going over the disk multiple times or any of that kind of stuff when we're doing integration. So the 0 to 2 pi just gives us a one time around the circle. This is a very nice description compared to what we had when we were working in rectangular coordinates. There we'd have x squared plus y squared equals a squared. We'd have to maybe solve and all that kind of stuff. All that we end up doing here is just saying that r and theta are between various numbers. We can actually generalize this a little bit. We could look at, say, one circle out here, but another circle inside of it, where we look at the region between these two circles. This is a shape that's called an annulus. And if we say the inner radius here is a, and the outer radius is b, this would just simply be the set of all points r and theta, where r is between a and b, and then theta will use the same limits of 0 to 2 pi for theta. We could even look at just part of our annulus. So let's say we have here we have one inner radius, maybe that's a, an outer radius of b, but instead of going all the way from 0 all the way around to 2 pi, we're just going to go from some angle, let's say it's alpha, to some angle beta. This is what the book is referring to as a polar rectangle. I don't know if it really does have a more proper term for it, but we're going to be working with these enough, and this is a good enough term because what the description of such a region would be the set of all points r theta, where r is between a and b, and theta is between alpha and beta. This is exactly the way we set up our rectangles back in 15.1, where our x was between two values and our y was between two values. This is basically just playing exactly the same role that rectangles played in rectangular coordinates. We can actually even look at a few other regions that would be troublesome in rectangular coordinates. Just a couple quick ones. So let's say we have, let me redraw that. Let's say we have a circle, so still a circle, but we're centered at A0, and we have a radius of A. So it's going through the origin. Such a circle can actually, the circle itself is given by the equation r equals 2a times cosine of theta. So that has a very nice, easy description in terms of one trig function. and the radius. And we don't have to do anything like work with squares or anything of that sort. So not on, not only are we're going to be working with circles that are centered at the origin, but we can work with other circles as well. Though it's a little bit limited in which circles have very nice descriptions. Just some random circle out in nowhere space might have a worse description than this one would be. But there are a lot of other things that we can work with. Another example. This time I'll leave out any radius or anything like that. But let's look at r equals cosine of 2 theta. This is a kind of nifty looking shape. And let's see if I can draw it here. Actually, a little bit better than I might have expected, but it's supposed to be a little bit more symmetric than that. Let's actually graph this thing so you can get a better idea of what it looks like. GeoGebra doesn't really work too well with polar coordinates. It doesn't recognize r and theta as variables for graphing. What I'm going to use is I'm going to basically turn r equals cosine of 2 theta into a parametric curve. So remember, x equals r cosine theta, y equals r sine theta. I'm going to replace that r with my formula. So I'm going to replace r with cosine of 2 theta, which I'm just going to use t for theta. So cosine of 2 theta times cosine of theta. Then we have cosine of 2 theta times sine of theta. And then theta is going to go from 0 to 2 pi. So that's what the curve is supposed to look like. And this is frequently referred to as a rose curve or rose petal curve. This would be the rose with 4 petals. And I'm not going to go any deeper into how those work. If you want to, the book did talk about them back in the Calc 2 polar coordinates section. We're just going to move on from here, because what we're concerned about here is how do we use this in integration. In essence, what we want to do is we want to take some double integral, let's say over some polar rectangle here, and a function f of x, y, and we want to essentially replace the x and y with our formulas, r cosine theta and r sine theta. Basically, what we're doing here is a substitution. And this is actually an example of a more general technique that we will talk about in section 15.9. Unlike that section where we're going to have a more general formula, so we don't have to rederive everything from scratch, here we are going to derive that formula similar to how we did it for rectangles. So like I said here, for now at least, we're going to be looking at R being a polar rectangle. So just kind of draw in our what we had. This is our R. Going from A to B on our radius, and then alpha to beta on our angle. Now, similar to rectangles, what we're going to do here is we're going to divide up our polar rectangle into a bunch of polar subrectangles, and basically into a grid of them. Let me get that out of there, because I want to go ahead and draw in some various different radii. Basically, we're dividing up our radius into multiple things. So let's say maybe we have like A, R1, R2, all the way to some R m minus 1, and then B. So a whole bunch of little different radii between A and B, and then also a bunch of different angles between alpha and beta. So let's say alpha, theta 1, theta 2, to some theta n minus 1, then beta. And then we have a bunch of polar subrectangles. Let's say Rij. This whole thing is R, but one of these little sub ones is an Rij, where this is just the set of all points R theta, where R is between Ri minus 1 and Ri, and theta is between theta I or not I, but j minus 1 and theta j. Of course, here we're treating, say, A as R0, B as Rn, M, and so on and so forth. But we just have a whole bunch of them indexed by I and j. On each of these polar subrectangles, we would take, say, a sample point. So some point in that polar subrectangle, we have our sample point. Maybe write this as Rij star and theta ij star. And we would use the value of this function at that point as a height of some volume. Of course, the function f takes in values x and y. It doesn't take in r and theta directly. We're going to have to use this formula here. So our heights is going to be the function at Rij star times cosine of theta ij star, and then Rij star times sine of theta ij star. And then our volume is going to be this height times the area of the base. But what is the area of the base? What is the area of a polar rectangle? How do we figure out what that is? Well, let's look at in generality. So we want to start with, well, first of all, everything is based off of a circle, the area of a circle. Shouldn't have to remind you that that is pi r squared. Next, we'll move on to what we call a sector. So a sector of a circle, you can kind of think of this as like that is a badly drawn picture. Think of this as like kind of a pizza slice or a pie slice, where we take an entire circle, but then we cut out a piece of it. This point here is at the origin, and then this is our circle up here, and these are just rays out from the center to the circle. This will have some angle theta, and we have some radius r, and we want to know what is the area of such a thing. Well, we want to think about this as kind of a proportion of the circle. How much of the circle are we talking about? Well, if we were to go all the way around the circle, that would be an angle of 2 pi. So what we're really looking at here is theta over 2 pi of the circle. That's the proportion of the circle that we're looking at. So we're essentially going to take our area of the circle and multiply it by theta over 2 pi. Of course, the pi's actually do cancel each other out very nicely, but we still have the 2 on the bottom and the theta. So the area of our sector is 1/2 of theta r squared. If we want to look at the area of our polar rectangle, What we want to think about there is, what if we had a sector, but then we cut out a sector from it with a different radius? Let's say the radius of the little one is A, and the radius of the bigger one is B, coming from our idea from our polar rectangles from before. Well, there we're essentially taking, we call this theta again. We're going to be subtracting the two formulas for the area of the sectors. We have 1/2 theta b squared minus 1/2 theta a squared. And of course we can go ahead and factor out the 1/2 theta. So that is the exact formula for the area of a polar rectangle. Now, it's not exactly the formula that we need in order to make everything work. What we want to do here is give a way of finding the area of Rij that will actually make everything work out the way we need it to. And in order to do that, we kind of, instead of just saying theta here, we want to say this is a difference between two angles. So let's say the area of, actually, I might even put this as delta A, delta Aij, the area of Rij. It's 1/2 theta. The theta here is actually going to be beta minus alpha. That would give us the angle that we have there. But I'm actually just going to go ahead and write that as delta theta. This difference in thetas. B squared minus A squared, that's not delta R. We might write that as delta R squared or something like that, but that's not really too helpful. Instead, what we actually want to do is factor this difference of squares. We have B minus A times B plus A. B minus A is actually the difference in our R's. It's the delta R that we would expect. But what about the B plus A that we have here? What does that represent? Well, actually, we're going to combine the B plus A with the 1/2. We're looking at A plus B over 2. Now, this should actually remind you of an average. We're averaging the radii of the points in this sector. You can say this is the average radius. I might call that R bar. So we have well, actually, we don't have the 1/2 anymore. We have an R bar from the B plus 8 over 2. I'm going to go ahead and move the delta R here. Then we have the delta theta. Unfortunately, that's still not quite exactly what we want it to be, because we don't really have R bar as something that's being worked with in any of these subrectangles. But what we're going to do is, since we're going to take all these polar subrectangles and shrink them down, we're going to turn this into a limit. We're going to be looking at ones where there's not a big difference between our R values. In fact, when we look at our sample point here, the Rij star is not going to be very different from this average radius. So we're going to actually approximate our area using Rij star instead of R bar. So this formula here is exact. This one here is approximate. But that approximation gets better as we go through our limit, as we take these polar subrectangles shrinking down to nothing. And that's good enough for what we're going to be doing with it. So we can get a Riemann sum. We have to sum over the i's and the j's, like we did before. We need to put in our function. So this would be f of xy. But remember, are we're not really putting x and y in there. We're putting this more complicated expression. We're putting in stuff with r times cosine, r times sine. So those are going to be our heights of our volumes that we're talking about. Then we put it in a dA or dAij, but dAij we're actually using this formula here, or at least approximating it using that. So you could say that our volume is approximately that, with a better approximation if there's a lot of polar rectangles, or polar subrectangles. As we take the limit as these polar rectangles shrink to nothing, as we let the number of them go off to infinity, this actually turns into a double integral. So here we have the double integral of our function f of xy over some polar rectangle r is just the iterated integral from alpha to beta and from a to b dr d theta, where we put r cosine theta and r sine theta into f. But notice we do have an extra r in here. That comes from the rij star that we got from our formula for our area of the sector, or the area of the polar rectangle. Don't forget this r when we go through our examples, or when you do the work on your homework. This actually will play a role in a lot of these problems. So just by basically changing the polar coordinates, we end up having this extra little piece. And like I said, when we look at this in more generality, when we get to section 15.9, we'll see where that r actually comes from. But for now, just think of it as an extra r that you need to include when you ever do anything with polar coordinates. Now, before we even get into any examples, I'm going to go ahead and generalize this the way we did in the last section. So we might look at a region where instead of just having r being between two values and theta being between two values, instead we actually have two functions. And when we work with polar coordinates, we almost only look at functions r of theta. So we might have some h1 of theta, r equals h1 of theta, and r equals h2 of theta as two curves in here. And then we have some limits on our theta that we're working with. So theta here is going from alpha to beta, like before. And we might want to see what is the double integral over a region like this. Let's say our region here, D, is the set of all points r and theta, where theta is contained between these alpha and beta, but r is contained between two functions of theta. Now, of course, we've set this up to look very similar to what we had when we worked with our type 1 and type 2 regions. In fact, you might even say, since the second variable here, this theta, is the one that's being put into the functions, this looks exactly like we had for our type 2 regions, just with a different letters. And so it really shouldn't be too surprising that we get to end up handling it just the same way we did with those type 1 and type 2 regions. We actually end up getting a very similar formula. And I'm not even going to go ahead and derive it for us. The book doesn't even bother to do that. We just get a very nice formula. So when our D is set up the same way that I had up here, then our formula for the double integral is just going to look like we had on the previous page, where we go from alpha to beta. For d theta, dr, we actually changed to having the two functions, h1 of theta to h2 of theta. And then we have the same integrand, f of r cosine theta, r sine theta, and then the extra r. So very, very similar kind of thing. And that's why we actually, in our formula here, I made sure to put the r in front. So we originally had the d theta over here. I moved the d theta to the back because, in general, we do want to put the theta in back because we like to only look at functions r equals a function of theta. We don't ever actually change. We never really set this up as theta as a function of r. That almost feels a little awkward to try to even set up. So we don't do that. All right. So this video's gone on for a little bit. I, I do want to do a number of examples like we did in the last section. We have a lot of things that we need to look at here. So I'm going to do those in its own video or maybe multiple videos like before. But hopefully here you can see that ultimately the formulas that we get are not that bad. They're actually pretty nice compared to what they could have been. So I'll see you in the next video. We'll work through some examples.